a real world use case where we applied our RFT platform to get significantly better performance than much stronger models with a very small number of labeled examples. So the task we're talking about today is function calling, which is a core agentic skill. And the core skill that we're gonna evaluate the model on is simply whether it can select the correct tool or not. And why function calling is important is, imagine my user had a workflow where they wanted to plan a trip, and they gave it tools like creating calendar events, looking up flight prices, or sending emails, all part of the organizational planning. Now, for the LLM to do this task completely correctly, not only does it have to use these tools correctly, but the use of tools and planning all depend on each other. And so any failure in any step of this chain can cascade down the chain and ultimately lead to an unsuccessful result for the user. And so in use cases like this, we want the model's accuracy to be 95%, 100%, 80%, 85% is not good enough, because even just adding 2, 3 steps to that plan reduces the end-to-end accuracy significantly. So the data set we're going to be looking at is this Glaive function calling data set, where essentially the LLM is given access to a set of tools in the system prompt. So in this case, we have a tool that is used to create a calendar event. And one important aspect to remember is that these tools also have required arguments and sometimes optional arguments. And so if you're going to use the tool, you have to supply the required arguments. And the user here asks to create a calendar event. And what we want the assistant to reply with is it can reason for as much as it wants between these think tags, and then has to output these tool tags and output exactly the inputs for the function, which is the function name and the arguments. And in this example, we only have one tool, but this data set can have one to 5 tools in each example. But the user message will only ask the assistant to use one tool at a time. So it's simpler than a lot of even more ambitious use cases, but it's surprisingly hard even for state-of-the-art models. So I'm going to first look at some of the common mistakes that even quote unquote more intelligent models make with this task. So one common issue is that the model will call a tool even when it has insufficient information. And so using the create event example, this message is an actual message from the data set, which is the user says, I want to create an event in my calendar. Now, the model should not use the tool at all. It should output the tool tags with no tool use within it, because it doesn't have any idea what the event title, start time, or end time should be, right? And you can see here a reply from Qwen-32B, and it correctly even reasons that it doesn't have the required information to fully use the tool, but it still goes and outputs the tool with these empty arguments, right? And even with prompt engineering, these mistakes still pop up. Now, another example of this with GPT-4o, and an example I consider more insidious, is we have this tool called check word count. The user asks, I have a text and I need to know how many words it contains. Can you help me with that? Now, clearly, the user has not provided the text yet. And so we don't want the model to use the tool quite yet. It needs to wait for additional input. But GPT-4o goes ahead and tries to use the tool, and it passes in this placeholder text. And this is even more harmful because you can imagine if you have a automated backend workflow using these responses in a chain, that you might actually go call check word count. You'll get a word count of 1, and then you'll basically be replying to the user with a nonsensical answer. And that can be very, very frustrating to users who expect much more intelligence from these models, especially in this routine sort of decision making that is a real bit important subskill in agentic workflows. So some other common mistakes are just like formatting mistakes, and one issue with these formatting mistakes is they happen infrequently, but enough to be irritating. 1 in 10, 1 in 20 results. So in the first one, the model outputs not just the dictionary we want, but this tool call keyword behind it, which will mean when we go try to automatically parse it in the back end, we're going to hit some errors. And the bottom one, you can see this more complex tool call, more complex schema. The model adds an extra write brace. So this again will not compile. And the only real solutions to handle this problem currently are either, prompt engineering, which tends to be a bit of a game of whack-a-mole, or some sort of structure generation library, which adds a bunch of complexity and even has been shown to affect model performance and accuracy downstream. Right. So with RFT, we're hoping that we can tackle all these problems by simply defining some really simple reward functions over a small number of labeled examples. And that's exactly what we're going to do. So the two reward functions we're going to define, one on correctness and one on format. So the format function, right, is just going to check the structure of the output. So does it have correctly open and closing thing tags? And we give partial credit for partially correct responses. And this really helps the model knows when it's heading in the right direction. And then we check if the tags are in the right order. So reasoning and then the tool output. Then we check there's only one set of each tags. So that the model, because one of the constraints we defined in the prompt for this problem is to only use one tool at a time. And then finally, we want to check if the actual tool call, if there is one, is parsable as like a dictionary and it contains a name field and an arguments field. For correctness, we have two possibilities. If the ground truth does not use a tool at all, then we'll get full credit if the model also chooses to use no tool. If the ground truth does use a tool, we first check if they both use a tool, we give a partial reward of 0.2. And then we give an additional reward of 0.4 for a total of 0.6 if the names match. And we finally bring that up to the full reward of 1 if the arguments also match. So really, it's that simple, right? And for the RFT training, there's only 20 labeled examples taken randomly from the initial data set. And the results are striking. So here we evaluated on 150 holdout validation samples. So starting from the left, right, the Qwen-32 billion model, which is an order of magnitude larger than the model we trained with RFT, which is the 3 billion size model, gets 83% correctness score with the exact same correctness function I defined here, right? And GPT-4 gets a similar score of 0.81. Now, surprisingly, even after adding the 20 same training examples as few shot examples in the prompt, GPT-4 does not improve. Upon investigating the results, it tend to make the same mistakes as before, calling tools when it didn't need to, despite examples showing exactly use cases to not do this. Now, meanwhile, the 3 billion Qwen model, right, out of the box, it gets a score of 0.6. And we would really love to use this model for this task because it's so much smaller and faster, and we can use it as part of a larger system and can really help reduce latency. So we might first check out SFT. And SFT, 20 examples gives you a great boost of 10%, but it quickly saturates. Even up to 2,000 examples, we just about get close to the larger models. And it's unclear how much more data will we need to even get to that 90%, 100% accuracy we really want. But with RFT, with the 3 billion base model and only 20 labeled examples, we get a 99% correctness. And, actually even training the model to get to that correctness only took about like an hour. So it's clearly not too difficult of a task for it, but RFT is the right tool for the job to actually get your model to perform.